Okay, we're going to finish up here, chapter 14, maybe, I think it is. 13? 13, that sounds like a good one. 13, 14 is the big one coming up. So we've been talking about, obviously, last time, solving equilibrium problems. And obviously, as we talked about last time, we definitely want to make sure we do our ICE table. Again, we saw a few different ways to go about solving these problems. Once again, you could have a sort of simple square root on both sides. You could also do the quadratic formula. And the last thing that we saw there was if you do have a small value for K, that means that the relative change that's going to occur in the reaction is going to be relatively small. And we would expect to have a lot of reactants still there at equilibrium. So in those situations where you do have a relatively small value of K, you can make an assumption that X is equal to 0. Remember, though, that when you sort of make that assumption that X is equal to 0 because of the small value of K, we do not get rid of all the X's. So it's always usually the X where you have kind of a number minus X or maybe a number plus X. Those are the X's that we really do get rid of. Anything that's pretty much like X by itself or 2X or something like that nature that started out with 0 in terms of the initial, we do not get rid of because we would have nothing to solve for. You do need to check it. Once again, we are going to use the 5% rule here. And basically the way that you check your assumption is you take the X value you got. So you take the X value that you got there. You divide it by really the initial concentration, which is usually the number you're going to either add or subtract it from. And you times it by the 100%. And again, if it is 5% really or less than 5%, then it is a good assumption. And that means that you can use the value that you got when you did that. If you do find, and it can happen, and it does happen, that if you do make the assumption, it may actually be more than 5%. So that kind of more than 5% or 5% or more is considered too big of a change to sort of ignore basically that X value being 0. That means you do need to go back again and solve it some other way. So as we talked about, that pretty much will mean for us that you need to go back and use probably the quadratic formula to do so. So it can definitely save you time on a lot of problems, but you shouldn't get into the habit of just assuming that it will work in every situation, because it will not work. So you got to make sure that you definitely do check it if you do that. The alternative to that is you don't have to make the assumption. You could just roll right into the quadratic if you like to do it that way, and just do the quadratic if you like. But again, it may save you obviously some time if you can make that assumption. And why do the quadratic formula when you might not have to do it, and a lot more room for error, obviously, going through the quadratic. But definitely make sure that you do check it. We finished, obviously, talking about what we talked about this morning. We talked about last time, which was Le Chatelier's principle. And remember that in Le Chatelier's principle, we basically have a system that's at equilibrium, and then you really do something to it to frankly mess up the equilibrium. So again, the equilibrium means that the rate of the forward reaction and the reverse reaction will equal each other. You do something to it and you mess it up, it will respond by either making more products, which is sometimes referred to as shifting to the right. It will respond by making more reactants, which is shifting to the left, to once again reach that equilibrium state of the rates of the forward reaction and reverse reaction equaling each other. Remember, again, it doesn't mean that you get the same amount of stuff that you started with. It just means that those rates will basically equal each other again. So again, some of those ones that we talked about that can obviously cause some shifting to occur in Le Chatelier's principle, concentration. So either we add more or we remove. And again, as we've talked about, when we do add more, it will shift the reaction away from whichever side you added it to. And that means if you add more reactants, you have a lot more reactants, which would really start the forward reaction to occur. And that's why you see more products being formed. If you were to add more products, what that means is you would have more products, and that would really kick off the reverse reaction to occur. which is why you would see more reactants being made in that case, or shifting to the left away from it. The other way that we could do, obviously, is remove something. And as you did today in the lab, you added something to an equilibrium reaction. And by adding it, you made perhaps a precipitate, which is what you should have saw, hopefully. And that is essentially removing something from an equilibrium reaction. That's basically one of two ways that you can usually accomplish that, making a solid, or as we talked about, if hydroxide or H plus involved, you can make water. But when we remove something, you could think of it as creating like a hole on one side of the reaction, and it will always go towards that hole to like fill it. If you want to think about it that way, you made a hole, you got to then fill it. So it's going to shift towards the side that has kind of the hole. The real reason, for example, if you get rid of reactants, is if you get rid of some reactants, what that means at that point, you now have a lot more products than reactants. They're going to start reacting because there's more of them. And that's going to cause, again, the reverse reaction to occur. It's going to go to the reactant side. If you remove products, the opposite is going to happen. You basically will then end up with really kind of more reactants than products. And that's going to cause the forward reaction to occur, which is why it goes to the product side. So however you want to remember that, like you made a hole, you need to fill it so it goes towards the hole. That's a good way sometimes to think about it. But ultimately, what we're doing when we kind of play with the concentration is either kind of kicking into gear the forward reaction, or we're kicking into gear the reverse reaction based on basically what you did to that equilibrium. Temperature, as we've talked about, is really the only aspect that will change the actual numerical value of the equilibrium constant. And again, what we're talking about there is a comparison of equilibrium constants at two different temperatures. So that's what we're talking about. At two different temperatures, the numerical value of the Ka will be different. But if you keep the reaction at a constant temperature, the K value should always be the same. Again, you'll get the same proportion of reactants to products. Temperature does work the same way as concentration, as we talked about. And really the key here, as we talked about earlier in the other day, is determining what type of reaction you're dealing with. Is it exothermic? Is it an endothermic reaction? And in most cases, that's the delta H value that you're going to really kind of look at. If your delta H value is negative, again, it's an exothermic reaction. If your delta H value is positive, it's an endothermic reaction. And one way that we sort of think about these things, maybe not correct in all aspects, but when we do have an exothermic reaction, we think of the heat as really a product here, or the energy as a product when our delta H is negative. And vice versa, heat is considered a reactant when we're dealing with a delta H that is positive. So once you really determine sort of what type of reaction you're dealing with, it works the same way. So again, if we were to increase an exothermic reaction's temperature, we would expect it basically to shift away from the product side and go to the reactant side. And if we were to decrease an exothermic reaction, we would expect it to come towards the product side. It'd be like removing heat or energy from the products. And the opposite would occur in an endothermic reaction. In an endothermic reaction, if we increase the temperature, would be like adding more reactants, which would kick off the forward reaction and we would make products. And if we decrease the temperature in an endothermic reaction, it'll be like removing reactants. So it'll come towards that reactant side. The other thing that we talked about is pressure, and really volume are oftentimes tied together. And personally, for me, I usually think about it in terms of volume. So as the pressure goes up, the volume goes down. And as the pressure goes down, the volume goes up. And really, the pressure going up on the case here on the left is because the volume went down. So it would shift to the side with the least number of gas molecules. And the pressure going down as a result of the volume going up would mean it would go to the side with the most gas molecules. So in this case, if you just think about in terms of volume, small volume, less gas molecules, larger volume, more gas molecules. And again, that obviously is reaction dependent. as to which side has more or less gas molecules. Again, you could simply just look at the coefficients in the balanced equation for anybody that has a G next to it and add them up, and you could determine, which side has more gas molecules or not. Lastly, we did talk about obviously a catalyst, and again, it does not obviously affect the equilibrium position. You'll just sort of get there quicker. Any questions on any of that stuff there? Yeah. Yeah. It depends on what type of reaction it is. So if it's an endothermic reaction and the temperature went up, that would be correct. It would shift away because temperature would be, or heat would be considered a reactant in that case. But it would be the opposite if it was an exothermic reaction, because heat would be considered a product. So if you increased it for an exothermic reaction, it would shift to the reactant side. So it depends in terms of temperature, what type of reaction you're dealing with. Other questions there? Okay, so let's just do a few more here before we finish it out. Let's say this guy had an H value that was negative for the purposes of this demonstration here. So if we added some H2, if we decreased the volume, if we increase the temperature, if I removed NH3, if I decrease the pressure, and if I, that's good, I think. All right, so will it shift to the right, to the left, or will there be no change? So take a moment or two for each of those and figure out what you think is going to happen here. All right, let's take a look. So starting with the first one, we're going to add some H2. Which way should it go? It should go to the right. So we're adding H2 with a reactant. That's going to basically make sure we have more reactants. So that's going to kick off the forward direction, and we should make some products in this case. We decrease the volume, which means should go which way? It also should go, in this case, to the right. When we decrease the volume, that means the pressure is going to increase, which means we kind of want to bring the pressure back down. So we need less gas molecules in the smaller volume. On the right-hand or left-hand side here, we have 4 gas molecules, numbers in front. And over here, we have 2 gas molecules. So in this case, it would shift to the right because of that. We increase temperature, it's going to go. It is going to go to the left in this case. We know this reaction, because the value of delta H is negative, is an exothermic reaction. Means that basically heat is considered like a product. So when we increase the temperature, it's going to shift to the left there. And that means that we would go it away. So shift there to the left-hand side. If we removed NH3 or ammonia, we would end up which way? It would also go to the right. Again, we're removing this. So if you want to think about it like you just created a hole on that side, that's going to kick off the forward direction and start to fill that hole with more products, basically. Lastly, here, we decrease pressure, which means the volume went up. And that means that we have more volume, which means we need to bring the pressure back up. We would need more gas molecules, and that would cause it to shift, in this case, to the left. In this case, yeah. Any questions on any of those there? Okay, let's take a look at a couple more here. Let's go. That's one we just did. Let's take a look at this guy here. All right. So let us do, decrease the temperature. We increase the volume, we add O2, we remove NO, and we add a catalyst. All right, take a look, see what you come up with here on these. Here you put it there. So in this case, if we decrease temperature, which way is it going to go? It is going to go to the left in this case. It is endothermic, which means our delta H value is probably a positive number. That also means that heat is going to be considered a reactant. So it's like removing reactants, kind of creating the hole on the reactant side. So it's going to go that way to kind of fill the hole if you want to think about it. And the next one, we're going to increase the volume, which means we would expect the pressure to start to come down in sort of the opposite way. And in this case, going to do what? It is going to be a no change in this case. Normally, what we would be looking for, right, is it would shift to the side with more gas molecules. But in this case, there is no side with more gas molecules. So it's like a push and nothing much is going to happen. So it would be a no change in this situation. We're adding more O2, which is a reactant. And because we're adding more O2, that definitely should kick off the forward direction. And that means that we would expect to see more products being made in this case. If we remove NO, it should go to the right as well. Once again, creating like a hole on this side. So we're going to head that way to fill it, and add in a catalyst would be no change. Any questions on that there? All right, one last little run at this here. All right, so we'll look at, let's say we have this reaction here where we did a little this plus some B goes to C in this case. All right, we're going to say that A is pink in color. I'm going to say C is blue in color. Here we go. All right, so we have a system that is at equilibrium here. So maybe we're starting a little bit between pink and blue. I guess that would be maybe like a purplish type of color, maybe. All right, so what color would we expect to see if we did the following? We add more C, we remove B, we increase the pressure. Also, what I want to know is this exothermic or an endothermic reaction? If this is the observation that I saw when I put my test tube in a hot water bath, it became blue. And when I put my test tube in an ice bath, it became pink. All right, take a moment. What colors would we expect to see? And based on your observations, is it an exothermic or endothermic reaction? So if I add more C, what color should I see? I should see pink. Add more C, it should kick off the reverse reaction, and then the test tube should become more pink. If I remove B, what color should I see? It should be pink as well. Once again, we would be removing this, which means it would shift towards that side and become more pink. If I increase the pressure, which colors should I sort of see? I should see blue. That means the volume is smaller, which means we do want less gas molecules. And in this case, we have 3 gas molecules on the left and 2 gas molecules on the right, which means it would shift to the right-hand side, which means we would see blue in this case. Any questions on any of those? All right, so based on some observations here, is this reaction exothermic or endothermic? It is endothermic in this case. So the first observation that we saw was We put it in hot water bath and it turned blue, which meant it shifted to the right. And since temperature works like concentration, the only way to shift it to the right would be to increase it, right? And that would mean that heat would have to be on the left-hand side of the arrow because we were increasing the temperature in this case, right? When we put it in the hot water bath, so we're increasing it. So the only way to do that would be it has there. So ideally, right, the second observation here should agree. So let's see if it does. In this case, we are removing energy, right, by taking it and putting it into an ice bath. And it turned pink, which meant it shifted to the left. And the only way for something to shift to the left would be it has to be on the left in this case because we're removing energy, which also agrees with our first observation. So in this case, both of them are telling us that basically the heat and energy is on the left-hand side of the arrow. And that would mean that it is an endothermic reaction. In this case, delta H should be a positive number. Yeah. Question on that. So when you analyze your lab today, they should agree with each other. Both your ice bath and your hot water bath should agree with each other in terms of it being exothermic action in this case of the lab. Question on Chatleir's principle. All right, that wraps up chapter 13. Also the last information on our exam, which is 1 week from today during lab time. We're going to take it. Yeah, so at 8 o'clock, be there, ready to go. All right. So then we're going to go off to chapter 14, so chapter 14 is exam 2 information. And frankly, we are now getting into the heart of the class here. Yes, this is the part that gives people the most difficult time is like this chapter. In a lot of textbooks, this chapter is 2 separate chapters, but your book put it all together in one ginormous chapter. So the first part of the chapter, I'll be honest with you, not too bad. But as we get to the second part of the chapter, when we start talking about buffers and titrations, that is really where a lot of the conceptual understanding does come into play. You need to understand what is happening in those problems in order to do the math part right. The good news is by the time we get there, we will have done all the math that you need to do. You just need to know how to properly apply it in the correct situation. So that's, again, what gives people really a difficult part as we get into buffers, titrations, and in the next chapter after this, solubility product and some other type of equilibrium. So we're going to talk about acids and bases here. So let's just start with the basics here of acids and bases. So acids have a sour taste. Things like vinegar is acetic acid. Citric fruits have citric acid in it. Really kind of the basic definition, as we will see, of an acid is really the ability to produce H+ ions in solution. Something that has that ability to produce free H+ ions in solution is really what an acid is. A base, on the other hand, they have a bitter taste. They do feel slippery. A lot of soaps and drain cleaners and those type of things, they're all basic type solutions. You could go to Home Depot and buy straight sodium hydroxide to clear your plumbing and stuff like that. It comes in a bottle that says be super careful. But a lot of those Drano and those type of things are bases. A lot of soaps are bases and those type of things. And as we'll see here, basically a base is something that will be able to produce hydroxide ions in solution. Those are your basic sort of definitions of acid and bases. And in each of these cases, this is H+ that's free in the solution, not attached to anything. OH-, again, free floating ions basically in the solution is what makes something either an acid or a base. And that's basically what Arrhenius basically said. He did a lot of work with electrolytes, and electrolytes are guys that break apart into ions and conduct electricity. So his definition, like I said, is a substance that can produce H+ ions. Now, in acid-base chemistry, pretty much H+, which is the hydrogen ion, and H3O+, which is the hydronium ion, which is a polyatomic ion, They're pretty much used interchangeably. So basically, H plus is the same thing in acid-base chemistry as H3O plus. And that goes for both formulas when you write equations and also like formulas as well. So personally, for me, I use H plus most of the time. So really anywhere I put H plus, you can put H3O plus. It's basically going to be the same thing. It's really the acid part of the solution. Arrhenius base, as I mentioned, is something that will produce our hydroxide ions in solution. So H plus, H3O plus, pretty interchangeable. We'll talk about here in just a second why maybe you would get H plus versus H3O plus. It just depends on sort of how you want to write an equation to show an acid breaking down. So a more general definition, and actually we'll look at that right now. Actually, I want to just show you the difference here. If we took an acid like hydrochloric acid, which is a strong acid, because it's a strong acid, you could show what's really happening with the acid in solution by just simply showing that it's going to break apart into H plus and Cl minus. It's a strong electrolyte, a strong acid. It's going to 100% break apart into H plus and Cl minus. In solution with hydrochloric acid, you do not have any HCl units still together. They've all 100% basically broken apart. Another way that you could show what we just showed here, which is really sometimes referred to as just the dissociation of an acid, is you could react HCl and you could include water in your reaction. And in this case, what's going to happen is our H plus is going to be sent over there from the acid, and you would get H3O plus and Cl minus. So essentially, both of these reactions are correct. A lot of times people will just show the top reaction or equation, but you could show the bottom equation and it would be correct as well. So if you do include water in your acid dissociation equations, that's how you'll produce H3O plus. If you just simply show the acid breaking apart, you would just have H plus. So again, they're interchangeable. Both of these equations basically are just showing hydrochloric acid going for a swim and is going to break apart into its ions, basically, is what both of these are really showing. Any questions on that? All right, so before we get too far into here, just to make sure everybody's on the same page, let's talk just a little bit, and hopefully it's going to be a review of how to properly name acids, right? So you don't say like this thing over here or that like acid type looking thing. So hopefully this will be review, but just in case, really when you name an acid, right, it's all about oxygen and whether or not the acid contains oxygen. By the way, when you write formulas for acids, they are typically have the aqueous symbol next to it that implies it's a solution and those ions are floating around. If your acid does not have oxygen, so no oxygen in the formula, the name should be hydro something ic acid, right? So if we took HCl, this would be hydro, and this negative ion would be chloric acid, right? By the way, the cation for all acids are what? The cation for all acids is H plus, yeah? The positive ion always for an acid, right? If you had HBr, that would be no oxygen, hydrobromic acid, yeah? So if you do have an acid, it has no oxygen in it. It always should start with hydro. The middle part is really the negative ionic acid. If you do have oxygen in your acid, yes, these are sometimes referred to as oxyacids because they contain oxygen. They will also contain most likely a polyatomic ion. Everybody's favorite, right? And if you remember, most polyatomic ions end in one of two ways. They end in "ite" or they end in "ate," right? Those are the two common ways that polyatomic ions end. So if the answer is yes, and your polyatomic ion ends in "ate," your acid name will be something ic acid. So like HNO3. NO3 that has oxygen in it. NO3 is NO3 minus, which is nitrate. So this would be nitric acid. H2SO4. SO4 is sulfate. This will be sulfuric acid. Now, if your answer is yes, it has oxygen and your polyatomic ion ends in ITE, your acid will start with something and end with OUS, acid. So if we have something like HNO2, NO2 is NO2 minus, which is nitrite. This would be nitrous acid. H2SO3. SO3 is SO3 2 minus, which is sulfite. This would be sulfurous acid. The reason we have two hydrogens in H2SO4 is because sulfate is a -2 charge, right? So to balance it out to 0, because it's really an ionic sort of situation, you need the two hydrogens, right? So that's why we have that there. Question on naming. That should sound familiar, I hope to you. Yes. I don't know why they took days to tell you that, but that's how you guys name those guys. All right. So now you won't just say like that thing, hopefully, right? Said hopefully. All right. So the Arrhenius definition was a good sort of starting point in terms of acid and bases. He did only really focus in on, when he did it, a lot of strong electrolytes like strong bases that actually had hydroxide in the formula. Not all bases will have hydroxide in the formula. So a more generic definition of an acid and base was one that was come up by guys named Bronsted and Lowry. And the Bronsted-Lowry definition of an acid and a base is an acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. A proton is H+, by the way. Yeah. And that's because hydrogen has how many protons? It has one proton. How many electrons? One. How many neutrons? None. Yeah. So hydrogen only has a proton and an electron, and the way you become positively charged is you lose electrons, right? So that leaves it just a proton. So in acid-base chemistry, H+ is referred to a lot of times as a proton, but it is the H+ that we're talking about here in both of these cases. So here's an example in this case of ammonia and water. And in this particular reaction, what's going to happen is actually the water is going to act as the acid, and it's going to send over an H+ to the NH3. The result of that is we will get NH4+ on the other side, and we will produce hydroxide in this case. And that would make this an acid or a base overall. This solution, it would be basic. Yeah, we're producing hydroxide. So a really first key thing that you should think about when you look at these reactions is if you end up with hydroxide on the product side, probably going to be basic. If you end up with H3O+ or H+ on the product side, probably going to be acidic. So those are key things to keep in mind. Now, that means here that NH3 is our base and H2O is our acid in this case. And the consequence of the Bronsted-Lowry definition of acid and base is it actually will create some partners on the other side of the arrow. And in this case, this would be our conjugate acid. And this OH minus would be what is referred to as the conjugate base. Now, the acid and base are always found on the left-hand side of the arrow. The conjugate acid and conjugate base are found on the right-hand side of the arrow, and they are related to each other. The only difference between them and the only difference that you can have is actually this difference right here, is 1 H plus is the only difference that's between them. So if we look at the base here to the conjugate acid, the difference here is it has 1 more H plus. And if we look at the acid to the conjugate base, it has 1 less H plus. And that is the H plus we see right here being transferred from one to the other. So 2 important things here is, in order for something to be what's sometimes referred to as an acid conjugate base pair or a base conjugate acid pair, the only difference is an H and a plus. Now, the H is pretty easy to think about, but what messes a lot of people up is the plus part. Does my charge change if somebody gives away an H plus versus and accepting an H plus? The charges of everybody does change. So when we look at this guy here, which basically accepted the H plus, he basically became 1 more positive than he started with, right? Because he gained a positive charge. The water here with lost the H plus on the other side became actually 1 more negative than it started with because it lost a positive. So when it lost a positive, it has more electrons, right? So it becomes kind of like 1 more negative than it started with. And that's why this is OH minus over here. So the charge part of it's really important. And it's something that people frankly screw up on most of the time, is that positive part of it. They're very much focused on just the hydrogen either being added or subtracted, but you do need to adjust the charges of everything to make sure everything comes out correctly there. Any questions on that there? So here's an example here. Here's water. And this is water actually reacting with another water. So in one case, water is an acid. In the other case, water here is a base. So in this particular case, he would send over an H plus. The result of that is we will form OH minus, and we will form our hydronium ion here as well. Now, earlier we saw water acting as a acid in that case. In this particular case here, where we wrote this reaction, our hydrochloric acid is our acid. Our water is acting as our base in this and accepting the H plus. And again, the result of this is we will get H3O plus and Cl minus. Now, the acid here would be related to this guy, which would be the conjugate base. The base here would be related to this guy, which would be the conjugate acid. The only difference between those guys is that 1 H plus. This guy has 1 less H plus. This one has 1 more H plus. Now, again, regular acid and bases on the left-hand side of the arrow, our conjugate guys on the right-hand side of the arrow. And this reaction that I just wrote, in the reaction that we see here and the reaction that we see in the previous one, we have seen that water in some cases acted as an acid, and in other cases it acted as a base. And there are certain species that can act both as an acid or a base, depending on the situation. And things that could act as both an acid and a base are known as being amphoteric. So an amphoteric substance is a substance that can act as an acid or a base. So water is an example of that. It has the ability in certain cases to act as a base, has in certain cases the ability to act as an acid, and that is what basically the definition of amphoteric basically means. Any questions on that there? All right, so let's take a look at some here and see if they are conjugate acid base pairs. So for each of these that you have, which of the following would be conjugate acid base pairs? So take a moment and see if they are related to each other. Okay, let's take a look. So the key to determining if they are related to each other in terms of really the Bronsted Lowry definition is the H plus. And once again, that should be the only difference between the two things. If it is anything other than just one H plus, it is not going to be a pair. So let's take a look at this one, HCl, and I don't know why books write it that way, but ClO minus, right? All right, so in this case, the difference between this guy and this guy is an H plus, but there's also a difference of a oxygen that this guy has and this one does not. So because of that, they would not be pairs. So that guy would not be pairs again, because there's more than just an H plus difference. H2SO4 and SO4 2 minus, are those guys pairs? The answer is no, they are not pairs, because the difference between this guy and this guy is 2 H pluses, too many. It could only be one H plus, and that's the only difference. So those guys are actually, they are related to each other, but they are not related to each other in terms of it being a acid conjugate base pair. How about ammonium and ammonia? They are, again, the only difference here is one H plus, so that is a winner so far. Again, you could either take the H plus off of this guy and you should end up there, or put the H plus on this guy and you should end up there, whichever way you want to kind of look at it. We got H3O plus and OH minus. Are those pairs? Those are not pairs. Again, the difference here is actually a couple of H pluses as well, so they are not pairs. And obviously, none of the above would be incorrect, since 3 looks like a winner in this case. Question on that there. Now, to answer maybe the question you may have, but you didn't ask, which is about this guy. So that guy there does come from H2SO4, which is a diprotic acid, and a diprotic acid means it's got 2 hydrogens it can give off. Now, you may be deceived by what you learned maybe in the previous class or a previous class. We oftentimes look at the overall reaction when we think about sulfuric acid, for example, breaking apart. But hydrogens actually do come off actually in a stepwise fashion. They come off basically one at a time. So in this situation, what would happen is the H2SO4 would dump off one hydrogen and make HSO4 minus. The next step that would take place is actually the HSO4 minus would dump off another hydrogen to make SO4 2 minus in this case. So what you might be familiar with or looked at or seen before is if we add these together, that guy and that guy cancels, and it gives us that H2SO4 gives us 2 H pluses and SO4 2 minuses. And that is the overall reaction that is taking place, but it does happen in a stepwise fashion. That is why when we look at something like this guy and this guy, are they partners? They are partners. The only difference between them is one H plus. So if you put the H back on the guy on the right, you get 2 H's. Plus 1 and minus 1 gives you 0, which gives you the guy on the left. So those guys are partners. HSO4 minus and SO4 2 minus, are they partners? They actually are partners as well. The only difference between those two is 1 H plus. Again, if you take off the H from the guy on the left, you're left with SO4 minus. And when you take off the H, is actually a plus. So you become one more negative, and it becomes SO4 2 minus. So those guys in green on either side there, these two guys would be partners. These two guys would be partners. But if we jump like we did in this question from here to here, That's basically a two-step process there, and it would not make them partners in that case. Question on that there. Okay. So let's try this. We're looking for the conjugate acid for the guy right here. Right answer should be up there, hopefully. Let's see. What is the conjugate acid for that guy right there? So let's take a look. If we have this guy here, we know that we want to put on either an H plus or take off. So either add an H plus or remove an H plus in this case. So in this case, we are looking for the conjugate acid to this base. And the important thing to think about is the relationship that we talked about, which is an acid and a base. On the left-hand side, the conjugate acid, right, and the conjugate base. Now, in this case, it did ask us for the conjugate acid. And what we know in terms of partners is this is the relationship, right? Those are two things that are related to each other. So if we are looking for the conjugate acid, that means what we are looking at is a base, and the Bronsted Lowry definition of a base is it should accept, right, an H plus, which means that is what we would want to put on there. So we would add on an H plus here, and that would get us, I think I left off a couple of things there. I left off the H, which would be good there. There we go. That looks better. So we would add an H onto there and a plus, and that would give us C6H5 NH3 plus, which, as you correctly said, would be number 2 there. Yeah. So sometimes it's helpful in a lot of problems. They will not tell you, hey, this is an acid, this is a base. They will just simply ask you to write the formula for the conjugate acid or conjugate base. So if you think about it backwards of where it came from, and just use the Bronsted Lowry definition of either an acid will donate off the H plus or a base will accept it, you'll be able to do that. All right, so take a moment here for this particular one and write the conjugate acid for this guy, and also write the conjugate base. So take a moment there and write both of those, starting with this guy. Okay, let's take a look. So once again, in this situation, the decision is add the H plus or remove the H plus. So we'll start with the guy on the right here. We're going to look for the conjugate base starting with this. So once again, if you're not sure what you're dealing with, you do know that you want to end up with the conjugate base, which if we follow the pathway back here, that means what you are looking at that point is an acid. And an acid would mean, based on Bronsted Lowry definition, you should donate the H plus. So that means we should remove the H plus. So in this case, when we get rid of the H, we're left with a CO3. And once again, it's not just the H, but the plus is important here. So when we remove a plus, we become one more negative, and we will end up with carbonate, basically here would be the conjugate base. Any questions on that one there? Now, if we're going to do the guy on the left there and starting with the same guy, we're looking for the conjugate acid. So much like the previous example, we are looking for the conjugate acid, which means if we follow the backwards thought process here, that we are looking at in this case is it is going to act as a base in this case. Definition of a base is somebody that will accept the H plus. So in this case, we're going to put the H plus onto this. When we put the H on, we end up with an H and a 2, a CO3, plus 1 and minus 1 equals 0. So we end up with basically carbonic acid here, H2CO3. Question on that there. So again, a lot of questions, they won't tell you it's an acid or base. You got to kind of think about it backwards to determine it. And you can just use the basic definition of the Bronsted Lowry definition of an acid and base. This is also another guy here that can act as an acid or base. That is an amphoteric substance, just like water. you will come across a lot of these guys that have an H and a negative charge. Those are guys that really can, in a lot of cases, act either as an acid or base because it has the H to donate, and it also can accept the H plus because it has a charge as well, and it has kind of room to accept the H plus. So a lot of those guys have an H and a negative charge, you know, they can kind of go both ways. And we'll talk about later on in this chapter how you determine sort of which way will it do it. Will it act as an acid? Will it act as a base? You could kind of make that decision actually a little bit later on as well. Any questions on Bronsted Lowry conjugate acid base pairs? Okay. Then as we talked about, water can react with itself, and it actually does set up an equilibrium. It is what's going on in all solutions that involve water. And because it could set up an equilibrium, well, we could write an equilibrium constant for it. But just like normal, we would not include, right, the water as it is a pure liquid in it. So really the equilibrium constant for this would be what is referred to as Kw, which would be the concentration of H plus times the concentration of OH minus. It actually has a value at 25 degrees of 1 times 10 to the minus 14. This is one of those formulas where you could also write H3O plus times OH minus equals 1 times 10 to the minus 14. So again, you can use H plus or H3O plus, whichever way you like. Once again, I'm going to personally use probably H plus. So the concentration bracket is molarity in this case. And we could use Kw, which is the ion product of water, to help us understand whether or not a solution will be acidic, basic, or neutral. So in this case, once again, it is 1 times 10 to the minus 14. We could rearrange this and solve for H plus. It would equal 1 times 10 to the minus 14 divided by the concentration of OH minus. Or if you have the OH minus concentration, it would be 1 times 10 to the minus 14 divided by the H plus concentration. Good news is it's basically the same calculation. You basically put 1 times 10 to the minus 14 divided by whatever one they give you, and it will give you the other part. You could think of the H plus part of this as the acid part, right, of the solution. The OH minus is the base part of the solution. The concentrations of each of those things run opposite of each other. So as the concentration of H plus increases, the concentration of OH minus decreases. So they do run opposites of each other. And obviously vice versa, as H plus goes down, OH minus concentration will go up. So you could actually calculate some numbers here for the H plus and the OH minus. And if the H plus equals the OH minus solution, that means actually they both will equal 1 times 10 to the minus 7 molar. It is going to be a neutral solution. So the solution will be neutral. If the acid concentration, the H plus concentration, is larger than the OH minus concentration, it will be an acidic solution. And if the OH minus concentration is larger than the H plus concentration, it will be a basic solution. So you could actually calculate both the H plus concentration and the OH minus concentration in the solution. You could compare the two values, and whichever one is larger, it will be either acidic or basic, depending. And if they're equal to each other, it will be neutral. It is extremely important in this chapter and all other chapters, but really in this chapter as well, that you make sure you are using your exponent button on all these calculations on your calculator. Otherwise, you will find yourself off by a factor. Yeah. So you seem, as we go through some of these things, and you're like, my number looks really good on the front part, but the times 10 to the whatever part is just off. It is probably the way you're punching into your calculator. So definitely make sure you use that EE button, that EXP button when you're doing these problems. All right, so let's try one here. What is the concentration of hydroxide in an HCl solution that has a hydrogen concentration of 1.3 molar? Okay, let's take a look. So here we would use Kw, which is our H plus concentration times our OH minus concentration, and equals 1 times 10 to the minus 14. In this case, we are given the H plus concentration of 1.3. We are looking for the OH minus concentration here. So rearranging and solving for the OH minus, that would equal Kw divided by the H plus. And that would be 1 times 10 to the minus 14 divided by 1.3 in this case. And that's going to give us 1 to the minus 14 divided by 1.3. Going to give us a 7.7 times 10 to the minus 15. This would be molarity, as it is a concentration unit. So we do need these units in there. In this case, is it acidic, basic, or neutral? It is acidic because the H plus concentration at 1.3 is greater than the OH minus concentration. So it would be acidic, which we would hope, because this is hydrochloric acid, right? So we would hope that guy would be acidic. If it's not, then definitely something probably went wrong somewhere there in the calculation. Any question on that one there? All right, let's try another one, I think. In a solution where the H plus concentration is 1.2 times 10 to the minus 6, what is the OH minus concentration in the same solution? And is it acidic? Equals 1 times 10 to the minus 14. And by the way, if the temperature wasn't 25 degrees Celsius, would this number change? It would, because it's an equilibrium constant value. So in most problems, probably 99.9% of the problems, you can safely assume, even if it doesn't tell you that it is 25 degrees, and you can use that number. If they do tell you by some chance that it is a different temperature, they probably either refer you to a table or give you a different value for Kw to use. But pretty much is a safe bet to use that. But just be aware, it is still an equilibrium constant, and it does change the value with temperature as it changes. So in this case, we are given the H plus. So once again, here we're going to look at the OH minus, which would be Kw divided by H plus. And that would give us 1 times 10 to the minus 14 divided by 1.2 times 10 to the minus 6. Making sure we use our exponent buttons when we punch that in there, it gets us an 8.3 times 10 to the minus 9 molar. Or if you have a lot of calculators, a bunch of zeros and an 8 at the end, as your calculator ran out of room, basically, if you're not in scientific notation. First off, any question on the calculation there? Is this acidic, basic, or neutral, this guy? So we are comparing, again, the H plus concentration to the OH minus concentration. And in this case, the H plus concentration is larger, and it would be acidic. And just in case, right, the negative part of this number, right, is important, because the -6 means you're going 6 places to the left and adding zeros, but the -9 means you're going 9 places to the left, right, and adding zeros. So when you have a negative exponent, right, the larger number is actually the smaller number, right, when you turn it into like a decimal type number. Any questions on that there? Okay. So the next thing we're going to talk about is the pH of a solution. And a way that we measure if a solution is acidic or basic is to use the pH scale and to calculate the pH. And the pH scale does run from 0 to 7 to 14. Below 7 is acidic. Above 7 there is basic. And really, truthfully, dead on 7 is neutral. And as you go from 7 towards 0, you're becoming more acidic as you go this way. And as you go from 7 up to 14, you're becoming more basic as you go in that direction. The way that we calculate the pH is we take minus our negative of the log of the H plus concentration, Once again, this is another formula that you can substitute H3O plus in there if you would like to. It's the same thing. Depending on your calculator, you need to punch this formula in a specific way, and all the other ones a specific way. If you have a display calculator, you should punch it into your calculator the exact same way the formula is written, negative, log, and then the H plus concentration, probably using your exponent button. If you have a non-display calculator, this one and all the other ones, you actually need to start with the number, then hit log, and then hit the negative. So you have to work backwards. If you're not sure what type of calculator you have, hit the log button. If it says log, congratulations, you have a display calculator. If it says error, congratulations, you have a non-display calculator if it says error. Yeah. So again, if you have a display calculator exactly the way it's written, non-display, this one, and everybody else, you got to head in the opposite direction. Again, here, if we calculate the pH, that's usually what we want to use to figure out if it's acidic, basic, or neutral. Why a pH of 7 is neutral is because exactly those concentrations are equal to each other. And if you put that into the pH equation, that is what you get for 7. So that there is no misunderstanding for us in here, we're going to roll with exactly 7 is neutral. If it's a little bit above 7, it's going to be slightly basic. If it's a little below 7, it's going to be slightly acidic. So there's no misunderstanding. 7 on the nose there for neutral. If it's acidic, it obviously will have a pH that is less than 7. And if it's basic, it will have a pH greater than 7. Should go that way. Now, speaking of using our calculators to calculate this, let's try one here. Actually, let's talk first off about sig figs and pH type of calculation. The number of decimal places in your pH type of calculation should equal the number of significant figures in your concentration value. So the number of decimal places that you should put out there for your pH or pH type of value should be the same number of decimal places as the number of significant figures your concentration has. So why don't we calculate one? What is the pH of a solution that has an H plus concentration of 2.5 times 10 to the minus 6? All right, so calculate that up, see what you get. I will as well, since I just made it up. Hopefully we'll end up in the same spot there. All right, so when we put this in, whichever way you're going, either negative log 2.5 exponent button, negative button, and 6, or going the backwards way, 2.5 exponent button, negative 6, log, and then the negative button. You should get on your calculator this number, 5.6020599991. So first off, hopefully you got a number that looks something like that. How should we report this? Should we report this as 5.6? Should we report it as 5.60? Should we report it as 5.6020599991? Which one would be the correct way to report this one? I heard 5.6 and 5.60. Thankfully, I did not hear anybody say this number here. Too many. All right, so what the rule is in this case, we will look at the concentration number. And this number here has how many significant figures? It does have 2 significant figures, which are those 2 right there before the times 10 part, right? So anything before the times 10 part is significant. The number of significant figures in our concentration value is not how many significant figures our pH should have, but it is how many decimal places we should have, which would be 2 decimal places. So the correct answer should be 5.60 in this case. So 2 significant figures in the concentration translates into 2 decimal places, not significant figures, but 2 decimal places in the pH value. We're going to talk about obviously going backwards as well, going from pH to the concentration. You would follow the same rule if you had 2 decimal places in your pH value. When you would calculate your concentration, you should end up with 2 significant figures. So it goes both ways as you're calculating it. By the way, to finish up on acidic, basic, or neutral, this one. It is acidic. It is less than 7 there. So it would be acidic. All right, any questions on that there? We'll lay it up, I think, for today.